Swayam Prabha. Digital India. Educated India.
Welcome to the 5th lecture of the series on mineral resources. Just to sum up, we were discussing some very fundamental attributes of mineral deposits, I would rather say, because we are already knowing now that deposit is the term that we use for the entities which actually are the ones which are from which we recover the minerals, where resource represents a generalized, more qualitative term in totality. In this lecture, we will try to build up the rationale for classification of this mineral deposit and see what kind of a classification we could propose. Before that, I would just like to continue on where we exactly quickly some of the points which we were discussing in the last class. We were discussing about the mineralogy and we were essentially trying to understand the texture, which basically can be defined as something as the intergrowth of minerals, more than one mineral in an ore sample of ore in the ore body. So, from the texture we were essentially trying to establish something called a paragenetic sequence, and this paragenetic sequence, when we study the texture, we are in a position to establish if there are the constituent minerals which are present in an ore, what is the time relationship, and also from that we basically try to establish the assemblages, or to be more precise, the equilibrium assemblages which we can see in that particular ore. So, whether there are many such equilibrium assemblages which could be thought of in terms of the paragenetic sequence. Sometimes the paragenetic sequence can be divided into the primary stage and the secondary stage, like the later alteration, which are very important in context of ore bodies, which we will see them later. But what exactly we are trying to the information that we want, because in the context of an ore body, we always would like to characterize the ore forming process in terms of the parameters, intensive parameters like pressure, temperature, and the compositional variables. So, the compositional variables, when our minerals are dominantly oxides and sulfides, we would always be talking in terms of the fugacity of oxygen, fugacity of sulfur, and so on. So, essentially these terms are nothing but the partial pressure, corrected partial pressure. If at this point of time we are not getting into the fundamentals of thermodynamics to define or to explain what this term is, for the time being, if we think that these are compositional parameters representing fugacity, the partial pressure, corrected partial pressure of oxygen, sulfur, or sometimes even carbon dioxide, as we saw in the last lecture. So, it is essential for us to characterize the ore forming process with respect to these intensive variables, so that we can interpret in terms of what was the broad physical process that was responsible in formation of this ore deposit. So, how it could be retrieved from the mineralogy? I will give you a very small example here. Suppose we have a mineral which is magnetite, and we also do have a mineral which is hematite. I know that this magnetite, where iron is present in both +2 and +3 form, whereas in hematite the iron is present only in +3 form. So, that means it tells me that going from magnetite to hematite, partial pressure of oxygen has to be increased, or the oxidation state has to be increased. So, what I do, I will just add oxygen to it, even though oxygen may not be available as free oxygen the way I am representing it, but I can represent the reaction in such a way that I can use this oxygen as an operator here. And so, I will put 2 here and 3 here. So, 8 plus 2 10. So, this is 9. So, I can make it half O2. So, this is something like magnetite plus half oxygen giving rise to hematite. So, if this is a reaction, then this reaction will have a equilibrium constant as log K corresponding to a particular temperature and pressure. I am not getting into any more details into it, as to, because we all know that when we put this log K will be equal to minus del G 0 by R T. Yeah, so del G 0 is equal to minus R T ln K. So, log K is coming from this del G 0. We are not, if we do not want to get into the details of this exercise. So, this is the free energy change, this is the gas constant, this is temperature in Kelvin. So, we get a log K value for this particular reaction. And now, this reaction, if I write, the log K will be the Fe2O3 raised to the power 3 divided by Fe3O4 raised to the power 2 into fugacity of oxygen, or I can write partial pressure of oxygen raised to the power half. So, we know that this is the K, we know that this is a mineral, solid mineral whose activity or the concentration of the activity is 1, concentration is 1, and this is also concentration is 1. So, here K becomes 1 by fugacity of oxygen raised to the power half, and if we take the log K will be equal to half minus half log FO2. So, I can, so if we take a diagram like this, where we put log FO2, because then that means here log FO2 will be equal to minus half log K, and I will get a single value. So, suppose in that case, if I draw a line somewhere here, this is the point, this is the line which will be dividing magnetite, which I will represent as magnetite here, and this is hematite as hematite here. So, here this is temperature is fixed and pressure is also fixed. Similarly, suppose I take a reaction, suppose I have in this particular mineral assemblage also I do have pyrite and pyrrhotite, magnetite and hematite. Okay. So, now suppose I have got pyrrhotite and pyrite. So, the reaction pyrrhotite is FeS. So, I will write FeS plus half S2 is equal to FeS2. For this reaction, since exactly following the procedure that I have followed here, where the solid activity are 1 and it is actually reduced as a fugacity of the gaseous species, this also will be reduced to only the fugacity of the sulfur based on the log K value that I would have got at the particular temperature and pressure, and I can draw it also as a line which will be here on this axis, it is log of fugacity of sulfur. And suppose I have got pyrrhotite FeS and I will add oxygen, and this will give me Fe3O4. So, this is 3 and this is 2, and I will get 1.5 S2 here. So, this reaction is one where oxygen and sulfur both are involved. So, if I write the log K of the reaction, which we can elaborate through our some of the exercise which I may be giving you, that this particular reaction, since it both involves oxygen and sulfur, I can always put them into a straight line equation where log fugacity of sulfur will be a function of the log fugacity of oxygen, and I can get these corresponding points and get this boundary. Similarly, I can also get the similar reaction written for pyrite and magnetite, and I can get this boundary, and also already I have explained how the magnetite hematite boundary could be plotted. So, here what basically we get here is that, suppose in a situation in our mineralogy we are getting pyrite, pyrrhotite, magnetite and hematite, and then we know that with these principles we could think of that whether our paragenesis is actually is in correspondence with these principles or not. So, here I can represent that this is a chemical system where it belongs to Fe, S and O, is a 3 component system. In this 3 component system, where temperature and pressure are fixed, where the 2 compositional variables are fugacity of sulfur, that means sulfur and oxygen. So, any point which will be called as an invariant point, there I must have, if I put nu is equal to C minus P plus 2. So, here the number of components are 3, and if I put an invariant point where nu is equal to 0, then this will become the number of phases will become 0, this is minus 3 plus 2. So, minus, so the number of phases will be 3. So, P is equal to nu minus nu plus C. So, nu is 0. So, C plus 2. So, here since we have pressure and temperature both fixed, so number of components. So, here actually it reduces to the Goldsmith's mineralogical phase rule, where nu is equal to C minus P. So, in an invariant point where nu is equal to 0, the number of components will become number of phases. So, here in this particular invariant point we can get pyrrhotite, pyrite and magnetite, all 3 which will be coexisting with each other as an equilibrium pair. So, now basically what I am trying to explain is that mineralogy constitutes the most important fundamental attribute of an ore, where the compositional variables like the fugacity of sulfur and oxygen could be constant, and if we go on increasing the number of components, for example, in case of iron, sulfur, oxygen, we add copper, or go on adding many other components. So, we will be ending up with the phase relationship amongst them, where we will be able to interpret the different assemblages in terms of the physicochemical parameters, which is important to us. And this texture study is that we draw the paragenetic sequence of deposition, and it is not only helpful for our interpretation in terms of the origin or the processes, understanding the process by which the ore has formed, it also helps us in the beneficiation process by looking at the intergrowth of the ore minerals, retrieval of physicochemical environment of ore formation, and integration into the picture of crustal evolution. So, basically what we try to do, the information of the intensive and the variables, compositional variables that we retrieve from study of the mineral paragenesis, we along with the intensive parameters like pressure and temperature, we integrate them and then try to formulate or try to understand the physicochemical environment in which the ore deposit form. Okay. And a large class of deposit owe there. So, we understand further characterization comes from quantification of several physicochemical parameters like temperature, pressure, fugacity of sulfur, oxygen and other compositional parameters. A large class of deposits owe their origin to the activity of a hot aqueous fluid that could be of diverse source, which we will be discussing in the part of this lecture series will be devoted to hydrothermal deposits. And after we characterize this deposit with respect to its broader specific geological setting, host rock, mode of occurrence, morphology, which is a very important attribute of ore deposits, physicochemical environment, the source, because the basic questions that we pose whenever there is a mineral deposit in its origin, in terms of its origin, that where from the metal has come, where from other constituents like sulfur, where from it has come. So, these are the basic queries that we address. It is quite important to study ore deposits and formulate the genetic models. It is just not only for academic purpose, but also that we from the very beginning we have stated the basic objective of this course, that the scientific knowledge, the knowledge base that we generate, that we acquire and that we rationalize on the formation of the mineral deposits, we utilize the knowledge for the exploration of these deposits in areas where such deposits are not known to be existing. And okay. So, at this point of time, suppose that we have some idea about the mineral deposits in terms of the broader processes, endogenic and the exogenic processes that give rise to mineral deposit formation. So, now then we will use that to classify the mineral deposits. So, here is a one such scheme for classification of the mineral deposits. Since we know that the three broad processes, the exogenic and the exogenic and endogenic together, could be like a magmatic process, sedimentary process, metamorphic process, and this magmatic process could be divided into two, volcanic and the plutonic, because we know that these are somehow different in their the mode in which they operate. This is the so the plutonic or the subplutonic process or the volcanic process. The plutonic process might give rise to rocks of diverse composition, felsic, intermediate and mafic. The felsic rocks generally are the granitic rocks or the carbonatite. The granitic rock will encompass the range from granite to monzonite, quartz diorite or diorite type of composition, and generally we observe that mineral deposits of copper, molybdenum, tin, tungsten, uranium and gold, they are associated with these felsic intrusives, plutonic, subplutonic kind of process. There can be intermediate composition rocks which give rise to the iron, titanium, vanadium oxide deposit, and they give rise to a very important class of deposits which are the chromium, nickel and platinum group metals, which are associated with ultramafic magmatism. And in the sedimentary, we have a classification, broad classification of the sedimentary environment into detrital and chemical. So, in the detrital, the deposits that we discussed about the uranium quartz pebble conglomerate or the placer type gold deposits, they will come under this category, the detrital mechanical concentration. We have uranium, gold, tin, thorium and tungsten deposits which generally are found in this environment as a result of detrital sedimentation process. We have chemical sedimentation, which we have seen the large class, the banded iron formation and also manganese and uranium. They do result from the chemical process, the chemical sedimentation in response to change in the physicochemical environment from transportation to deposition, as we saw uranium being transported only in the +6 state and being deposited when the condition is reduced to +4 and so on. We could also add up a little bit up to the sedimentary environment, because some process which could also go on along with the deposition of sedimentary rocks in a basin, which we call them broadly as the syn sedimentary exhalative or the syn diagenetics, or people used to, or they are popularly were known as the SEDEX, syn sedimentary exhalative deposit or syn diagenetic. Quite a good amount of the base metal resources, lead and zinc, come from these deposits, and the weathering related deposits, mostly aluminum and nickel, and enrichment process which happens on the surface operative process, purely exogenic in nature, thereby the kind of beneficiation, Earth's own beneficiation mechanism that we discussed, our weathering process which give rise to also sometimes that these weathering process they do not give rise to the primary mineral deposit, but they can enrich an existing deposit to a higher concentration, which we will discuss them in the later part. And biogenic and the metamorphic, we see that either it could be a contact metamorphic or contact metasomatic type of process, which give rise to the skarn deposit, which are very rich sources of tungsten, molybdenum, tin and iron. Even there are gold skarns also, which are there very generally named called by the name skarns. Regional metamorphism, we all know that is because of the materials which are produced. There is no much of metallic mineral deposits that known to be resulting directly from the process of metamorphism, but graphite, aluminosilicate minerals like kyanite, sillimanite, andesite, they do result from this process. And under the metamorphic group, we could also include something, the process which would be metamorphogenic rather truly metamorphic. Something in addition to metamorphism also takes place there, exemplified by most of the gold deposits occurring in older geological terrains. We will look at their characteristic in more details. And under the volcanic category, we can have a volcanism that is taking place on the ocean floor or the island arc or within the continents. So, the ocean floor island arc, we have seen examples of them, like giving rise to the volcanogenic massive sulphide deposits, which are comparable to the present day mineralization process, which are observed on the mid-oceanic ridge systems, and are also believed to have older analogues, like the example which I gave in case of the Noranda deposit in Quebec or Cyprus deposit, copper deposit. They are all volcanogenic massive sulphide deposits. And in the continent where there are volcanism, there are rich mineralization of gold, silver and base metals. And if you look at the tectonic map, you could delineate something which is labeled as the Pacific Ring of Fire. In the Pacific Ring of Fire, all along we get volcanic islands, and in those volcanic islands like the Indonesian island, Papua New Guinea, Lihir Island and the Japanese island arc. So, we see that there are some very rich mineralization of base metal and the precious metal. They go by the name as the volcano associated epithermal deposit because they are near surface process. So, this is one scheme of classification. This is definitely not very complete. You could possibly add a few more of them, but conforming to the broad framework of the classification scheme that we are adopting here, mainly a process based. If you look at the textbooks, like I referred to book of Jensen and Bateman, there the classification scheme is far more wider. It also takes into consideration some very rare type, but sometimes important deposit which is resulting from the process of sublimation. We all know sublimation. This is deposition from vapor. So, this generally we see some deposits of sulfur as well as some very low volatile metals like mercury, arsenic and antimony. They are occurring, they are mineral deposits, they occur in hot spring kind of situation where this process could be broadly categorized as sublimation, in addition to the one which followed as our previous scheme, magmatic, sedimentary, hydrothermal, metamorphic, and sometimes evaporation process also is becomes important in giving rise to some specific mineral resources. For example, gypsum, which is a mineral for our cement industry, and so this only comes from the evaporite beds which result by the evaporation of seawater in landlocked basins. and here it is this because the name is a little bit long, this is supergene oxidation and secondary sulfide enrichment. So, this is essentially a process by which pre-existing ore deposits become enriched, that is how the name supergene sulfide enrichment is proposed, and they are controlled by the exogenous process, because the surface weathering process is controlled by the precipitation, the surface water, and which is by it acquires its chemistry in relation to the rocks and the soil. And of course, one thing we should remember, that the exogenous process is very important because it forms soil, and soil is very important for us as a resource, because many things depend on it. And residual concentration, which we have already discussed as a mechanism by which deposits can form. Good example is the bauxite deposits occurring in many of the continents. Mechanical and residual concentration is already we have seen where our detrital sedimentation process and contact metasomaticism of skarn. So, this is a scheme that was followed in textbooks like Allen, Bateman and Jensen, where the deposits are described. But our course of lecture will not be exactly following this, but we will be following the broader process that we have. In the literature of mineral deposits, there are many ways also to classify them in more genetic term. Genesis, what I mean by the origin, the processes involved in the origin. So, a particular class of deposit are known by the term as syngenetic. Syn generally stands for the same time as the formation of the rock in which they are occurring. So, syngenetic essentially means that the mineral, that the ore body and the rocks in which the ore body is occurring, they formed at the same time, not only the same time, but with the same process. So, this is how the syngenetic process, where your magmatic deposits giving rise to chromium, nickel, platinum group of metal, and in the mafic, ultramafic rocks, they very unambiguously belong to the syngenetic category, where the rock, the ore itself is a product of the magmatic process, magmatic crystallization process. Similarly, the iron which we see in the form of the banded iron formation, and also the manganese in sedimentary horizon, different sedimentary basins, they are also syngenetic. They do form the part of the sedimentation process itself, chemogenic, metamorphic, and the volcanogenic massive sulfide deposits which we saw them which form on the ocean floor. We can also categorize them as syngenetic, although the in terms of the time, but in terms of the process, because it requires a little bit more than exactly the seafloor basalt which is coming on the mid oceanic ridges to give rise to this deposit. So, the ones which come as epigenetic, epi stands for the term that anything that is not related in time. So, it is something later or something different. So, epigenetic means the mineral deposit came into existence any time later than the time at which the rocks, associated rocks formed. The examples are many, rather the number of mineral deposits which come under the category of epigenetic are much more than the ones which come under the syngenetic. These epithermal veins means still there are words like epithermal is still being used. They generally represent the near surface processes. A large class of such deposits give rise to copper, lead, zinc and precious metals. They are present in the brittle deformation zone in the crust, as we discussed in our introductory lecture, and the metamorphogenic gold which we just discussed, that along with the metamorphism there is something in addition that happens, which we will see what that addition thing is. In shear zone hosted situations where there are crustal scale deformation in the form of shear zones or faults, and deposits associated with unconformities, because they also where unconformities were the locales which were more favorable for formation of certain deposits which will be later than the time at which the host rocks formed. So, these deposits which were representing as epigenetic, all these in red, have one thing in common, that they owe their origin to the activities of hot aqueous fluid, that is water rich, which will be one of the major topics that we will be covering, the hydrothermal deposits, because the number of such deposits are too numerous compared to deposits which form from direct magmatic process or any direct sedimentary process. So, involvement of a fluid which is there in the crust is very important in formation of the ore deposits. So, sometimes we also do classify ore deposits based on their morphology into stratiform and stratabound. Stratiform, the term is pretty straightforward, that they are very much conformable to the strata in which they are occurring. The examples are the banded iron formations or the chromite layers in ultramafic rocks. It is basically this term comes from the morphology, the exact form in which they are occurring. The term stratabound, so these are the stratiform will always be syngenetic by default, whereas the stratabound deposits are diverse, pretty complex mode of occurrence, but they are generally observed to be confined to some particular stratum in a sequence. Say for example, if we have a sequence of sandstone, shale, limestone and is intruded by a felsic magmatic rock, we will find, or we generally find, that the deposit which forms will be very much confined to the limestone horizon. So, we conclude that there must be some chemical relationship between the one particular stratum in the sequence to the formation of the ore body, and that is and they are mostly epigenetic rather than very few exceptions. Previously the ore deposits were also classified into hypothermal, mesothermal, epithermal and telethermal. These were all basically based on their spatial relationship to a magma, because previously the belief was that all the deposits that we see are actually result from magma. So, the deposits were classified based on their spatial relationship to the magma. The hypothermal were the deepest ones, 3 to 15 kilometers, and the highest temperature 300 to 600 degree centigrade. Mesothermal being 1.2 to 4.5 kilometer. Epithermal is more surfacial, where the temperature also is much less. Telethermal was only those deposits which were spatially far more away or distantly from the intrusive body or the magmatic body, which is supposed to be responsible in giving rise to the mineral deposits. So, what we generally see is these classification schemes are all incomplete and tentative, and but they just provide a broad framework on which we can base our theories of orogenesis, and there are scopes still there to revise the deposits in the classification scheme. And also there are instances in which a deposit which is earlier classified into one particular category, later on because of its because the changes or the difference in the attributes that is observed later on could also be classified differently than what it was done originally. So, in summarizing the weeks, so we have defined what mineral resources is, conceptualized the control that is exerted in their occurrence in the quantity and quality. We familiarized ourselves with basic terminologies, ore body, ore mineral province, mineral belt. We attempted to rationalize the distribution of mineral resources in space and time, and we tried to, or we saw how these mineral deposits, what we gain by studying these mineral deposits, hypothesize them, understand their origin, and then propose a classification scheme. And so then we will, so this is basically providing us a broad fundamental insight to these ore deposits to continue looking at them in greater details, and to although will be very limited in the understanding the orogenesis, and then we will see them all other aspects in due course. Thank you.